In this video we're going to look at ways to convert from differential signals to single-ended signals, which will lead us into a pretty tricky amplifier analysis. Though there are lots of interesting ways to use differential signals, we're ultimately interested in building an op-amp, and op-amps have single-ended outputs. So we need to be able to convert our differential signal into a single-ended signal. One super easy way is pictured on the left here. We can just take the signal from one side of our differential amplifier. As long as our load, whatever this is hooked up to, is high enough resistance, this won't change the operation of our amplifier at all. So the top level takeaway of this approach is that it's super easy, but we throw away half of our gain. We can see that clearly if we look at our single-ended output signal VO and compare it against the differential output signal VODM over 2 that we'd get if we were treating this thing as a full differential amplifier. VO is clearly only half of VODM, and the downward swing on this node isn't going to be reflected in our single-ended output. This is an okay trade-off if you need simplicity, which is to say throwing away half our gain is an okay trade-off if you need simplicity. But we're going to see an amplifier that lets us capture our whole differential mode voltage gain very soon, like even before I'm done with this slide. However, before we do that, let's think about the small signal parameters of this amplifier. The differential inputs don't know where we're picking signals off of this amplifier, so there's no reason that R in DM would be any different than a normal resistively loaded emitter coupled pair. And we can make the same argument about the common mode input impedance. The common mode voltage gain starts to look a little weird because we have to write a new definition for it. So this equation here defines the gain as the ratio of our single-ended output to the common mode input. Okay, it's a weird definition, right? We're no longer going from VOCM to VCM, but it doesn't change the physics of our circuit at all. Whether we're measuring our output on just one side or the other, when we're putting in a common mode signal, we expect these to move up and down together. And so because those two are still at the same voltage, we can make the exact same common mode half circuit and wind up with the same common mode gain, minus RC over 2 over R tail. The differential gain is a bit different from the emitter coupled pair with two outputs, because we have to use this new definition where we're comparing a single-ended output against a differential input, but this is against our full differential input. And as we observed up here, VO is only half of our differential output. So our differential voltage gain is half of the differential voltage gain that we'd get if we were taking an output on both sides. So it's minus GMRC over 2. Finally, we don't have separate differential and common mode R-out values because our output is single-ended, so there's just one R-out for this circuit. However, the single-ended output is easy enough to approximate in this case. If we look at this node, we see RC going up to a small signal ground, and then we're looking down into a collector down here. And the collector probably has a resistance of at least RO, and then there's a bunch of other stuff in parallel with it, or excuse me, in series with it, that might raise the impedance higher. So we can say, alright, this is probably just RC, it's good enough for now. Though it's worth noting that if we were to try to calculate the impedance looking down this way, we'd be in for a sort of mathematical ordeal, because the tail node connects to both the tail current source and the whole left side of the circuit. So there'd be something pretty complicated hooked up down here. Okay, I promised you an amplifier that made use of our full differential gain, and this is it. Here we load the emitter coupled pair with a current mirror instead of loading it with resistors. That mirror is going to capture any current that Q2 conducts and then reflect it around to the output node here, which results in a factor of 2 increase in our gain. That's pretty cool, and we'll analyze that behavior in a minute. But first, It's worth noting this type of circuit, the mirror-loaded emitter-coupled pair, is extremely common and useful, so much so that it's called an ordinary transimpedance amplifier. And you know something is common when it has ordinary in its name. Starting in on the small signal behavior of the amplifier, we can make the same arguments we did before about the input differential mode and common mode impedances. They don't know what's hooked up on the collectors, and so our load here doesn't affect them. However, this amplifier has a lot of other surprises. For instance, it's not immediately clear how to calculate either the common mode gain, or the differential mode gain, or the output resistance, or even the large signal output operating point, right? Usually we think about current flowing through a resistor and causing a voltage drop to set VO, but we don't know that here. We'll spend the next 2 slides figuring out Rout and AVDM, which are pretty crucial to using this amplifier. VO actually can't be solved analytically because it is the interaction of these 2 transistors. And it's very sensitive to differences in these transistors, so process variations or temperature differences between them would cause VO to wander around. So as a consequence, you usually set VO using feedback when you're using an amplifier like this. And we'll ignore AVCM for now. But the one thing to take away about it is that it winds up small. Okay, so we can make a small signal model for this OTA, going from here to here. And we notice right away that our small signal model isn't symmetric. We have a diode-connected Q1 device on one side, and a pretty much normal-looking Q3 on the other side. That means we can't fall back on half-circuit analysis, which is a shame. We're going to start our analysis strategy by noting that any change in small signal current at the VO node, so if a little more was injected into it or a little was taken out of it, has to flow to ground through whatever the output impedance of the amplifier is. Because VO is our output node, we could replace the whole amplifier with just the output impedance to ground here. So just glancing at our circuit topology, that output impedance is probably kind of big. Like it's RO3 in parallel with whatever we see looking down here. So the whole thing is probably on the order of RO. Fine. That means we probably got sort of a big gain, and if we could guess how much current is being injected or removed from the VO node, and we could guess Rout, we could get a sense of what that gain is. We'll start by trying to find the current change into the VO node, this Rout. Writing KCL at the VO node, we see that the extra current that gets injected here that needs to worm its way to ground is primarily contributed by GM3 and GM4. Those two will add some current and then it has to run away. The GM4 current is easy enough to calculate. Our input is still differential, which means the tail node is still a differential ground, and so GM4 is being controlled just by minus VDM over 2. And we put an additional minus sign here because the current is being sucked out of the VO node. GM3 is a bit trickier, but it's worth noting that we can simplify it by thinking about current mirrors. The 1 over GM1 impedance here represents Q1, which is the left side of a current mirror. So that means any current that flows into this 1 over GM1 branch is going to flow out of GM3. We can see that clearly by noting that we're calculating this by taking the current through GM2, VDM over 2 times GM2, multiplying it by the impedance it sees, which is basically 1 over GM1, like this RO and this RPi3 are big compared to it, in order to get VBE3, and then multiplying that by GM3. Because GM3 and GM1 are part of a mirror, they cancel out, and we see that the GM2 current appears magically at this GM3 generator. So specifically, if GM1 and GM3 are matched, they cancel out, and we see that GM4 and GM2 are being added together. Both of these sides of the amplifier are contributing to our output current. And simplifying further, if GM4 and GM2 match well, then we find our output current is about equal to minus GM times VDM. So we're capturing our full differential input voltage in our output current. Hooray! So we know the current going into R out, but now we need to find a value for R out. And you might be able to guess that that's going to be a little bit involved by looking at the horrible small signal model I've drawn on this side, which I promise is just a redrawing of the differential small signal model on the left. You can see that by looking at, say, GM3, which is just hanging off of our Vout node to ground, or RO3, which is just hanging off of our Vout node to ground, or RO4 parallel GM4, which is hanging off of our Vout node to this big emitter node that's now represented here. And you could carry on that sort of matching analysis. This is the same thing as this. So with that model drawn, we can launch into small signal analysis. But before we do, I want to warn you that I'm never going to expect you to do this kind of big derivation under duress. However, you are responsible for the results of this derivation, which you can already see up on the title of the slide. The output impedance of this is about RO over 2. So understanding this circuit is much easier if we break it into a few pieces using Thevenin resistances. Specifically, RTH1 and RTH2 are both values that we can calculate to make our life easier. RTH1 looks down into a 1 over GM pattern because the control voltage for GM2 is in parallel with it across this compound resistor and labeled VBE24. That means we can use our usual 1 over GM pattern, which is this resistor plus this resistor divided by 1 over GM RO. So we have RO2 plus 1 over GM1 divided by 1 plus GM2 RO2. And that falls in parallel with all of the resistances in the compound resistor. This term is the smallest by far, and if you evaluate it closely, it's approximately 1 over GM2, because these RO2 terms cancel out. Knowing RTH1 makes it easier to find RTH2, which is just given by a left-right pattern controlled by VBE24, since this is the VBE for both GM2 and GM4. We know the current running in the RTH1 branch down here. Excuse me. So this is a left-right pattern, and we see RO4 plus RTH1, which is 1 over GM2, plus GM4 times 1 over GM2 times RO4. If these GMs cancel out, then this is about 2 times RO4. Knowing both RTH2 and RTH1 makes it easy to find VBE24. We know the current running down the RTH2 branch is given by VT over RTH2, and that current all hits RTH1, so we multiply it by that to calculate VBE24, getting this result. And knowing VBE24 helps us find VBE3, which it turns out is about the same as VBE24. VBE24 controls GM2, and almost all the current in this branch flows through GM2. So VBE3 is going to be given by that current multiplied by the impedance down here. So GM2 times VBE24 times 1 over GM1. And there are a couple of negative signs that cancel out here. This is negative and this points up. To say that VBE3 is about the same as VBE24. Which is great, because now we know what controls GM3 and we can combine all of our expressions. So we write KCL at the top node, and find that IoT is equal to the current in the RO3 branch, VT over RO3, plus the current in the RTH2 branch, VT over 2 RO4, plus the current in this GM generator, GM3 times VT over 2 GM2 RO4, per this equation. Dividing through by VT, we see something that looks sort of like a parallel combination of RO3 and 1 over 2 RO4, and if these GMs cancel, another 1 over 2 RO4. So you add those together, and overall R out looks like RO3 parallel RO4. And if these are about the same, R out looks like about RO over 2. So, whew, it's good to know that. Now, your instinct, there's a handy way of remembering this, which is that many people's first instinct when they see this is to think, oh, I'm looking into the output, I see an RO3 going up and an RO4 going down, so the output impedance must be RO3 parallel RO4. It turns out that's right, but not for the reasons you think. You have to go through this whole analysis to show that the left side of the differential circuit doesn't mess with your R out. And finally, combining that with our reasoning on the last page, the differential voltage gain of an ordinary impedance amplifier is about minus GM times RO over 2. So remember this R out and this AVDM value. I expect you to use them when we see these OTAs out in the wild. In summary, you can get single-ended outputs from differential amplifiers by either grabbing one side of a resistively loaded emitter-coupled pair, or by building a mirror-loaded emitter-coupled pair, which is called an ordinary transimpedance amplifier, or OTA. The mirror loads in the OTAs combine the GM of the input devices by reflecting current from the left side of the load over to the right side. And finally, the output impedance of an OTA is about RO over 2, so the differential mode voltage gain is about minus GM RO over 2.